Running a sensitivity analysis identifies which components have parameters critical to the measurement goals of your circuit design. To run a sensitivity analysis, you must assign tolerances to the parameters of the components in your design. We've already set tolerances in this design, and to check the tolerances we can go to PSpice, Advanced Analysis, Assign Tolerances. A netlist will be generated and the assigned tolerance form is displayed. Notice in the global list we've set a tolerance of 10% in both positive and the negative direction for the value of all the resistors in our design, and the same applies to all of our inductors and all of our capacitors. We've also set instance level tolerances on some of the capacitors and resistors in our design. If we select C2 in our instance list, we can see that we overrode the global 10% tolerance with a local 20% tolerance for C2. Similarly, for R4 we set our tolerance to 0, so its value will not be varied at all in our sensitivity analysis. We've also set some tolerances on the subcircuit parameters in our design for our diode. We set the breakdown voltage to have tolerance of 10% in both the positive and the negative direction. For our transistors, we can see that we've set the BF parameter, the maximum forward beta, to have a positive and negative tolerance of 40%. And if we scroll down, we can see that we've also set a tolerance of positive and negative 20% for K, the base to emitter depletion capacitor, and CJC, the base to collector depletion capacitor. To run the sensitivity analysis, we'll also need to provide a simulation profile. For this circuit, we would like to quantify the sensitivity of the 3 dB low-pass cutoff frequency at the output and the sensitivity of the DC gain. To do this, we must first run a standard PSpice simulation on the circuit and make sure that it behaves as expected. If we look at our simulation profile, we already have an AC sweep simulation profile that does a logarithmic sweep of the frequency starting at 1 MHz and ending at 600 MHz. Our AC simulation profile is already selected, so we'll run our simulation by selecting the Run PSpice icon from the icon bar. After the simulation completes, the probe window is displayed. We'll add a trace to the probe window by selecting Trace, Add from the probe window, and we'd like to trace the voltage at our output in decibels. We'll select the dB measurement in the Add Traces window and notice that our cursor is already inserted between our parentheses. Since our output signal was named out, we should be able to scroll down and find the voltage on that output signal and insert it into the dB function. We'll select OK and the trace is added to our probe window. The sensitivity analysis quantifies the sensitivity of specific measurements to tolerances in the design, so we must define the measurements that we'd like to run the sensitivity analysis for. From the probe window, we'll select Trace A, Evaluate Measurement to open up the Evaluate Measurement form. We want to analyze the sensitivity of the 3 dB low-pass cutoff frequency at the output of our circuit, so we can select the cutoff low-pass 3 dB measurement from the Functions in Macros section of the form where it is added to our trace expression, and then insert the voltage of our output net Vout. When we select the OK button in the Evaluate Measurement form, we notice that our measurement results spreadsheet is displayed and our measurement has been added to the spreadsheet, and we have a current 3 dB cutoff frequency of about 186 MHz. The sensitivity analysis will quantify the sensitivity of this cutoff frequency, 186 MHz, to the tolerances of the components in our design. We'd also like to analyze the sensitivity of the DC gain. So again, we'll select Trace A, Evaluate Measurement to open the Evaluate Measurement form, and we'll select the max function and we'll measure the maximum voltage in dB of our output net. When we select OK in the Evaluate Measurement form, the measurement is added to our measurement results and we could see that our current gain is 18.15 volts, and we'll be quantifying the sensitivity of this gain to the tolerance of the components in our design. We're now ready to run the sensitivity analysis, so we'll return to the capture window and we'll select PSpice, Advanced Analysis, Sensitivity from the Capture text menu. After the simulation, the PSpice Advanced Analysis, the sensitivity user interface is displayed and we have to import the measurements that we had created in our PSpice analysis. In the specification section, we click where it says, "Click here to import a measurement created within PSpice." The input form displays the two measurements that we created for our RC analysis. And we can select them both by holding down the Shift key and selecting them and clicking OK in the Import Measurements form. The parameters table displays all device properties that have a tolerance applied to them. We can see the values for the resistors, inductors and capacitors in the circuit, as well as our D1 inductor and Q1 and Q2 transistors. The parameters table can be sorted by double-clicking on any of the column headers. We make sure that our analysis is set to sensitivity in the Advanced Analysis user interface, and then we select the Start icon to run our sensitivity analysis. After the sensitivity simulation completes, the results are displayed. If we select the cutoff low pass _3 dB measurement in the specifications spreadsheet, we see that our original cutoff frequency was 168.5 MHz, and when we vary the components by tolerance, we have a minimum cutoff frequency of 105 MHz with a maximum cutoff frequency of up to 243 MHz. The sensitivity component filter lists all of the components in our design and the relative sensitivity for the parameters of that component. Relative sensitivity is defined as the percent of change in a measurement value based on a 1% change in the parameter value. Our 3 dB cutoff low pass frequency is very dependent on the value of our R1 resistor. Similarly, we can pick our gain measurement and see the sensitivity of the gain based on variations of the values of the components in our design. Our nominal gain is 18 with a minimum of 15 and a maximum of 20. When the tolerance of the components are taken into account, we can see in the sensitivity component filter that our gain is most sensitive to the value of the R7 resistor. The sensitivity analysis identifies which components have parameters critical to the measurement goals of our circuit design.